Hello, and welcome to today's lecture on computational geometry. So, in this lecture, we're interested in a number of different aspects related to computational geometry, which of course is also very much related to lab number 3. Or is it 4? Lab 4. Sorry about that. So basically, we will go through a number of primitive operations on computational geometry primitives. We will talk about polygons, for example, how to compute the area of a polygon. We will talk about convex hull and also about closest pair. So if we start with the primitives, so as you're all well aware of, I mean, there are things like points, which you can represent in a Cartesian coordinate systems with an x and y. We have lines, which you can define by a linear equation, for example, and you have a line segment, which is then a segment between 2 points, so you can represent by 2 points. A polygon can then be represented by a sequence of points. So assuming these primitives, what are some of the operations we want to do? For example, to determine whether a polygon is simple, to determine whether a point is inside a polygon, check if 2 line segments intersect, and compute the Euclidean distance between 2 points, and given 3 points, determine whether they correspond to a counterclockwise turn. So we will go through most of these. So first of all, a bit of a warning. When it comes to computational geometry, people have a pretty good intuition of things in 2 and 3 dimensions. However, that is not the case for a computer. So we can determine, for example, looking at the examples at the bottom here, where we have 3 different shapes, geometric shapes. And now the question is to determine whether one of these is a simple polygon, which means that it has no crossings. And from our perspective, we can, through visual inspection, very easily see that the first 2 have this property, while the third does not. But if we, from the kind of computer perspective, just look at the sequence of x and y values, this is of course much harder. So I think it's important that the kind of human intuition that we have related to geometry does not apply to computers. And of course, when we come to higher dimensions, we also lose our intuitions. So trying to visualize a 10-dimensional space is extremely hard. So let's see another thing. So for example, to determine whether a point is inside a simple polygon. So a simple polygon, as we saw in the previous slide, is a polygon where there is no intersections. And here we have a theorem, which is already proved in 1886 by Jordan, which says that any continuous simple closed curve cuts the plane in exactly 2 pieces, the inside and the outside. So what we're interested in now, for example, is that given a polygon and given a point, determine if this particular point is inside or outside of the polygon. In this particular case, we can see, I mean, we can actually try to, let's see if I can get this. Can draw something here. So now we want to determine whether this point is inside or outside. So we can actually, trace. If I had been able to trace, that is. Sorry. So we can see here that we are able to go around and round and round and round and round and then out. So it means that this point is actually outside. And what we can see here is also that if we cross the boundary once, then we're on the inside. If we cross the boundary twice, then we're outside. So we can basically count the number of times that we cross this line. So inside, outside, inside, outside, inside, outside. And in this case, we realize that we're outside. Oops. So as you see, I'm a bit new to this. So we will clear. Okay, now clear all the drawings. Good. Yes, so basically now we need to determine the number of times that we cross the lines. So what we have is this question here, how many times, or rather, does a line segment intersect a ray? So the ray, of course, is from the point I want to check, and the line segments are the pieces of the polygon. So what we can do here is that we can actually basically, through a kind of standard algebra geometry, we can basically compute this. And then we can compute the number of times that we cross. And if this is an even number, then we know we're outside. If it's an odd number, then we're on the inside. So that we can do. So then we come to this counterclockwise turn. So this is a very useful operation, as we will see. So the question here is that given that we have 3 points, A, B, and C, does the angle, or does the movement from A to B to C correspond to a counterclockwise turn? And we can actually use this as a kind of sorting mechanism. And basically the idea here is to compare the slopes. So if we go in the leftmost example here, then we see go from A to B to C, and since which clearly makes a left turn. While in the second case here, we are actually making a right turn. In the third case, we basically have a straight line. So there's no real slope there, but still it makes a left turn. And then we have 3 examples where all of them are on the line. And here it's not really well defined whether it corresponds to a counterclockwise turn or not, because they're collinear. And actually, it turns out that it's somewhat tricky to compute this kind of things. And we also have the aspects of dealing with floating point precision, which adds another level of complexity when it comes to computational geometry. However, what we can see in this case is that if we compute the determinant of these 3 points, then this actually corresponds to twice the area of the triangle. And it also turns out that if the area is greater than 0, then it's a counterclockwise turn. If the area is less than 0, then it's clockwise. And if it's exactly 0, then these lines are collinear. So this gives us a very straightforward way of computing whether 3 points correspond to a counterclockwise turn or a clockwise turn, or if they're collinear. So very convenient and simple to compute. Yeah, and here we have an example of how we can use this counterclockwise turn. And this is that given 2 line segments, do they intersect? Of course, we can put up the equation for these 2 line segments and basically compute if there is a point in which they intersect or not. Or we can check if the endpoints of one line segment are on different sides of the other line segment. And that we can do through four calls to the counterclockwise turn. So basically, we check how this corresponds, and then we can determine whether where the 2 line segments intersect or not. So useful. So then we come to polygons. So polygons are extremely useful in many respects. And one thing that we need to to do is to be able to compute the area of a polygon, and that we can do using this formula. So basically, you add up the x values, you subtract the y values, and then you divide by 2. If you do this for all the n vertices, then we actually get the area of the polygon. And here is just an example that you can look at yourself. There is another interesting way of computing the area of a polygon. And if the case is that all the vertices are at integer positions, they have integer coordinates, then there is something called the Pick's theorem, which states that the area is equal to the number of interior points plus half of the number of points on the boundary minus 1. So in this particular example here, there are 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points on the boundary. So R is 12, and there are 40 points on the interior. So it means that the area of this polygon is 45. And of course, a corollary of this is that the area is either an even number, an integer, or 0.5. So I mean, it can be half. So it's quite nice and useful. But probably the most useful thing to compute when we're talking about computational geometry is to compute the convex hull. And what we're interested here is to, given a set of points, we define that it's convex if for any 2 points P and Q in the set, the line segment between P and Q is completely within the set. So it means that whatever line you draw between the pair of points, it will always be within this closed set. So in the left image here, we see an example, and on the right, we see an example where it's not a convex set, because when you draw a line between P and Q, you actually leave the set. So what one can do is that given a set of points, you can find out what is the convex hull. So basically the smallest number of points so that it surrounds all of the other points, so that everything within that is convex. And this actually has very many applications. For example, find the shortest fence around a patch of land, or a number of positions, I guess. And it's also the smallest convex polygon enclosing all the points. So very useful. If we were to do this, what to say, physically, so assume, for example, you have a board and a bunch of nails in the board, and then you want to find out the convex hull. All you need to do is to take a rubber band and stretch it outside all the nails and let go, and it will automatically adapt to the shape of this of the nails. There is another way, and that's basically that you take a piece of string, you tie it to for example, the leftmost, outermost nail, and then you just turn it around clockwise or anti-clockwise around all the nails, and then we get the same result. So, so again, this is an example where intuition is very useful. But now the question becomes, how do we do this computationally? So we can make a number of observations. First of all, edges of a convex hull of P connect pair of points in P, which means that we only need to consider points that are actually in P. Secondly, the line between P and Q is on convex hull of all other points if all other points are counterclockwise of this line. So in this case, we can see that we have a line between P and Q, and all the other points are then counterclockwise of this line. So this means that we can have a brute force algorithm in n cube number of steps. If for all pairs of points P and Q, compute whether all other points are counterclockwise. If this is the case, then we know that this line PQ is on the convex hull. So of course there are some challenges here. For example, if you have 3 points on the line, then you need to deal with that. So this is a very naive brute force approach. Another approach is called the Jarvis march, and in this case you start with the point with the smallest or lowest y coordinate, so on the line here, and then you rotate a sweep line. So you basically sweep a line counterclockwise until you reach a point. And since this is the first point that you reach, you know that everything else will be counterclockwise to these. Therefore, you are sure that this pair of points is on the convex hull. Good. Now you just continue. So you restart your process from the endpoint, and you do it again. And now you find the second edge on this convex hull, and then you continue like that until you reach the starting point. And when you reach the starting point, you have then managed to find the convex hull of your set of points. Yeah, you can also do this by computing the angle between the current point and all remaining points, and then pick the smallest angles larger than the current angle. So this is another way of getting these sweep lines, and this will require n checks per iteration because you have to check against every other point. So it's quite expensive. And then we can also ask ourselves, how many points are there on the hull? So we say that capital N is the number of points, and H is the number of points on the hull. Then we can basically, then we know that the computational complexity of the Jarvis march will then be n times this number of h. So there are h points that we need to find, and for each of these h points we need to compare against n points. So therefore this is then the computational complexity of this Jarvis march. So how many points are there on the hull? It actually turns out, in the worst case, all the points can be on the hull. So basically this will turn out into a quadratic worst case solution. If we're interested in the average case, then we need to actually deal with a much more tricky problem from stochastic geometry. So for example, if we have uniform randomly placed points on a disk, then we will find out that the average number is n to the power of a third. If they're uniform at random in a convex polygon with a constant number of edges, then h becomes the logarithm of n. But for our purposes, we need to treat this as a n to the power 2 squared, order squared. However, there is a better approach, namely called the Graham scan. So again, we choose the point with the smallest y coordinate. So again, we start basically at the bottom, and then we sort all points by the polar angle with p, and then we get a simple polygon. So we basically just create a polygon with all the points in the set. And then we get something that we can see to the upper right here. What we next do is that we follow these points, and then we check do the last 3 points form a clockwise turn, then we remove them. If it's still a counterclockwise turn, then we keep it. So in this example, we can see that the first 3 points, or rather the second 3 points will, if we have both of the last ones together with the next one, then we see that that will form a clockwise turn. So therefore we remove these. And so basically we go through all of these and remove vertex after vertex until we only have a few vertices left. So this is then called the Graham scan, and it's very nice. And we can also implement this quite efficiently. There are also some interesting tricks one can do to speed up things, especially if you have very many points, is that you can basically select 4 points in your set and then remove everything that's inside of these 4, because you know that these 4 will at least be, I mean, everything that's inside this will definitely be inside a convex hull. And then if you have a quadrilateral, then you need to do 4 counterclockwise turn tests. If you have a rectangle, then you need to basically compare 4 points. So this is just a way to rapidly reduce the number of points that you need to consider. And then when you have removed a large part of the points, then you can continue with any of the other methods. So the final thing that we will be discussing is the problem called the closest pair problem. So here, what we're interested in is the given endpoints in the plane. Find a pair of points with the smallest Euclidean distance between them. I mean, it's trivial to see that we can do this using a brute force approach, comparing every pair of points and then choosing the smallest one of those. And this, of course, is clearly n squared. If we have a line, then we can sort the points on the line, and then that would be n log n. And then we can basically pairwise check the points, because we know that the shortest distance will be between any pair of points that are next to each other. And then we can do this in linear time. However, how do we do it in the 2-dimensional case? So the starting point here is to set up a divide and conquer algorithm. And this we can do, so assume that we draw a vertical line, L, that roughly splits the set of points into 2 sets, one to the left and one to the right. Now we can reduce the problem to, first of all, of course, recursively finding the closest pair in the left side and the closest pair on the right side. However, we still have the case that the closest pair might have 1 point to the left and 1 point to the right. So therefore, we also need to find the closest pair with 1 point on each side. And then now we have 3 pairs, and we take the smallest or the shortest distance pair. So the closest pair among these 3. So in this case, it would be 8. So of course, to recursively compute the closest pair on each side, we can do recursively. So what's tricky here is, of course, how do we efficiently find the closest pair with 1 point on each side of this line L. This may look like it's actually as difficult as the original problem, because you might imagine that all the points are within this delta distance of L. However, we can actually, we know that we can do better than this. So what we do is that we sort all the points that are at most delta distance either to the left or to the right from the line L. We sort them on their y coordinates. So now we get something like this: 1, 2, 3, 4, 5, 6, 7. Now we only need to check the distance to those lines, points that are at most 11 positions away, or rather, yeah. And why this number 11? Well, it's because if we draw a diagram showing this, we can see that if we split up this area here into half d by half, or half delta by half delta squares, we know that this stripe is 4 deltas or 4 squares wide, because it's defined it should be 1 delta on each side. We also know that there can only be points at least 2 rows apart. And why? Well, it's because by definition, this distance delta is the closest distance on either side of this. So it means that if they should be closer than that, then delta would have been smaller. So therefore, we know this. So we can then see that there is at most 11 points that it can be away. So therefore we know this. So it's 12 here, and of course there's only 1 point in each of the cells. So if we check all these other 11 cells, then we're definitely fine. It actually turns out that we can do this with 7, and that you can check yourself. So this then leaves us with the following method. So we basically have to sort the points, determine which side they are on, solve the closest pair problem for the left side and the right side, and then we delete all points that are too far away from the line L, and then we sort the remaining on their y coordinates, and then we scan the points in y order and compare them to the next 11 neighbors. And if we find a better one, then we're done. Or we're not done, but then we have a better estimate. And then we return the smallest such delta. And then we can prove the runtime complexity. So in the kind of, naive case, it's n log n to the power of 2. But we can actually remove this extra log n factor by sorting the x and y coordinates once and then be done. So we can save 1 factor. So this then turns out to be n log n method, which is huge. Actually, when it actually turns out that when we work with computational geometry, most solutions are n log n. So what this means is that often you need to do some form of sorting and then some form of comparison, and then we get the solution. So that was all for today. Next lecture is about combinatorics and probability theory. We'll see how that goes. Okay, thank you very much, and bye-bye.